you're not listening to the people sitting beside you. Okay. Grab your notes out if you haven't already. We're going to talk through the homework. We talked about some of these already yesterday. Huh? No. No bets. I don't make bets with students. I do make bets, but not with students. Okay, so number one. We did this yesterday. We've established which one of these the student was pulling harder in. They are equal. Okay, we looked at that yesterday. It doesn't matter if it's attached to a wall or a strong man. The wall is pulling back on the kid as hard as the kid is pulling on. Same here. Okay, gentleman at the back, Khalil. The strong man is pulling as hard on the kid as the kid is pulling on him. These two situations are the same. In the picture below, well, if these are the same, okay, let's have a question here. If these are the same, why do we play a tug of war against other people instead of just strapping rope to a wall? Because eventually other people are going to get tired, and that's when you make them feel bad about themselves. The wall is never going to. So there is a reason why we do one of these instead of the other, but practically speaking, as far as the forces are involved go, they are equal. In the picture below, two students kick the ball at the same time with the same force. What are the force pairs that occur here? So you've got the force of A on the ball, and then you're going to have the force of the ball back on the boy. Let's call this kid C. And then you're going to have the force of C on B, and then you're going to have the force of B on C. And the net force on the ball itself is 0, even though both of these guys probably broke their toes. Net force on the ball is 0. Cool, flip the page. Given the action force in each of the pictures, state the reaction force. Student pushes up on the bar, the reaction force is?
Bar push down on you.
Bar push down on you. Which is why eventually this gets really hard. The bowling pin pushes to the right on the pin. Sorry, the bowling ball pushes to the right on the pin. So what's the reaction force? Pin pushes the other way. Why does the pin go flying? Because it has less mass. So the acceleration of the pin is much larger than the acceleration of the ball. The compressed air pushes outward on the balloon. The balloon pushes, yes, backwards in on the air. And actually, how balloons and the pressure works is actually super complicated, I discovered over the weekend. Yeah. You would...
What's complicated about it?
If you had this is totally an aside from this. If you had a large balloon and a largely inflated balloon and a small inflated balloon of the same kind of balloon, and you attached them with a straw, and you pinched off their ends, what would you think would happen if you let go?
What do you mean?
Like they're attached to a straw.
Oh, and like their ends that like let them move.
And yeah, and one balloon is twisted so that the air can't flow freely. I've got a large balloon and I've got a small balloon. They're the same kind of balloon, so you don't have to worry about the difference in their plastics. If I let the air flow, which way would you assume it would go?
To the smaller balloon.
You'd assume it would go to the smaller balloon. Now, don't ask me to explain why this is true, because it's more complicated than I know. Because I was doing some reading and I watched an interesting video on it. But that's not always true. It depends whether the balloons were in the process of being blown up or deflated.
Why? What do you mean?
Because the material of the balloon itself has a sort of memory. It knows what was happening to it the moment you cut off the airflow. So if one balloon was being inflated,
no, that makes sense.
The air would flow, even from the smaller balloon, would flow into the larger balloon, because the plastic of that balloon knows it was being inflated, and vice versa. If this balloon was being deflated, it would, yeah. It's more. I watched it and I read some more stuff and I'm like, I don't understand and this makes me really uncomfortable. But balloons are weird. You'd expect the air inside the balloon to be at a higher pressure. That's not always true. It depends whether the balloon is being inflated or deflated when you take the measurement. It's weird. Balloons are weird, I discovered over the weekend. Naya, good afternoon. If you got to take the life of a fictional character, which fictional character's life would you want? Okay, think about it. Don't ask why, but a man in a loincloth is pulling on a rope being held by a monkey that is attached to a spring scale that is tied to a tree. It's involved. What are all the force pairs? Okay, so we got man, rope, monkey, rope, monkey, rope, scale, rope, tree, rope. That's everything Zaid said. Did he miss any? Sorry? Oh yeah, totally. I missed one. Scale, rope. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There it is. Because you got 6 objects. 7 objects. There you go. That's a better way to think about it. Okay. The last thing I wanted you to do for homework was this. How did this go?
Great until I got to like the table.
Great until you got to the table. That's pretty straightforward. What did we establish here? You set the masses apart. You took a measurement of gravity. What happens when you alter the mass of one of the objects? What stays the same?
The gravitational force.
It better not stay the same. Okay, if the mass increases, mass goes up of one of the objects, the gravity went up. Did it matter which mass you changed? No. So if one was, I could be honest here, there's only a little bit of judgment. Hands up if you just didn't do this. Okay. Appreciate the honesty. Okay, so here we are. I don't know why it makes noise. I don't feel like it's totally necessary, but it's going to make noise. So I've got a 100 kilogram mass. I got a 400 kilogram mass. Currently, and we're going to put it into scientific notation, the force of gravity between these two is equal and opposite. It should be. So as I increase the mass of this guy, let's say I go from 100 kilograms to 500 kilograms. I'm at 8.34 both ways. Now if I decrease this guy back down to 100, actually this one's at 400. Oh my gosh. Okay, that's enough. The gravity, it doesn't matter which one is the bigger one, the force of gravity is the same. So it doesn't matter which mass you change, the overall force of gravity is equivalent. So what happens when you change the distance between the objects?
Oh, that stuff like its gravitational force decreases exponentially.
Kind of? How do you know it's exponential?
Honestly, I heard the word chem class, so
Oh, so you're just trying to sound smart by using fun words.
Yes.
Okay. Let's see if we can figure out how you're more right than you think you are. It's not purely exponential. Let's figure it out. So how far apart are these objects? Oh. No, we'll get there. Does it matter which object you move? No. If this one's at the 3 and this one's at 6 and then this one moves out to the 7, it's 1.67. If I put this one back at the 6 and I move this one back to the 2, it's still 1.67. So it doesn't matter which one moves away, it still decreases the value. Now we're going to click on the constant radius button. This guy here, the constant size button. Does the radius have any effect on the force of gravity? Did I change the radius? No. So it has no bearing. Doesn't matter how big the object is, which is really interesting. So what then must matter? The only thing that matters of the two objects is their mass and what? And the distance between what and what? More specifically, what about mass 1 and mass 2? Because it's clearly not their surfaces. The surface distance is not the issue. The issue is their centers. The distance between their centers. Now, I'm going to move this guy back. Now, the distance between them is 2. Right? Is that right? Yes, it is. I'm going to make these both 100 for the sake of our... So glad I muted that. Okay. The gravitational field strength, or the force due to gravity between these two objects is 1.67 times 10 to the negative 7 newtons of these two 100 kilogram things, and you're going to learn today how this gets calculated. The question I want to ask you now is, we're going to kind of do 6. Well, let's talk about 5 and 6. 5 said to briefly describe an experiment you can run to determine how the mass affects the force of gravity. Complete the table below with the data you take with the mathematical relationship between the mass and the force of gravity. We'll do this briefly here. If my masses are equal, the force of gravity is this. What happens if I double one of the masses? What do you mean equivalent? Yes, the forces are always going to be equal to each other. But what is the force if I double? What do you think is going to happen to the force if I double one of the masses? But how is it going to increase? Let's look at it. Let's go up here to 200. How does that number relate to the first number? No, like exactly. You're doing this thing, Connor, where you're just kind of trying to use big words. Tell me concretely, what happened? What was the first value? What is this value? How are they related? Well, the net force is zero. They're equal and opposite. Again, don't get more complicated than you need to. This number is double the first number. First number was 1.67 times 10 to the negative 7. This one's 3.34 times 10 to the negative 7. What happens if I double both of them, do you think? How does this number relate to the first number? The first number was 1.67 times 10 to the negative 7. How does this number relate to that very first number? I have now doubled both masses. Is it? Did you shove it through your calculator? Verify that what you're saying is right. Naya did. You're saying he's right. So this number is 4 times the first number. So now we're starting to build a relationship. We know if we... So I'm going to go back over here. I'll jump back to that in a second. I'm going to go to the bottom here. The relationship between the force and gravity, the force of gravity, and the mass. If I double one mass, it doubles Fg. If I double both masses, it quadruples Fg. So Fg must be dependent on what as it relates to these two masses? How would that show up mathematically? Is it dependent on the addition of these masses? Is it dependent on these masses divided by each other? Is it dependent on these masses multiplied together? It has to be multiplied together, right? Because if I have Fg is going to depend on a mass times a mass, if I double one of these masses, if this becomes 2m, Fg will be twice as big, right? If I double both of these, it's going to become 4 times as big because 2 times 2 is 4. If I triple these masses, what's going to happen? Well, that's what we can verify. Let's verify that. If I triple both of these masses, what would happen to the gravity? Is it going to be 6? Let's take a look. Let's make each of these 300. How does that number relate to the first number? Now, this is 1.5 times 10 to the negative 6, and the first number was 1.67 times 10 to the negative 7. How are these two numbers related to each other? See, do you have an answer for us now? Oh, you didn't do this one? Okay. Does someone have an answer for us? How are these two numbers related? This number here and the first number we had. If I triple both masses, what's happened?
Well, it's not.
I want a concrete answer, Connor.
Well, it's increased quite a bit, or sorry, it's decreased quite a bit because.
Cool.
Well,
Which one's bigger, 10 to the negative 6 or 10 to the negative 7?
10 to the negative 6.
Is bigger, so this number's bigger than the last one.
Yeah, okay, but, okay, well,
Anyhow. Okay, keep going.
Basically, it's. Well, I don't know if I can do that.
What did Manuel say?
It's 3 times 3,
Which is?
9.
Manuel, did you verify that, or are you just looking at the relationship in your head? Do you know that this is 9 times bigger than 1.67 times 10 to the negative 7? You did it in your head? I don't know if I believe you. You did that in your head? You did that in your head? That's impressive. He's right. It has to be 9 times bigger. If it's a mass times a mass, and I've tripled one and tripled the other, 3 times 3 is going to give me that 9. So we've established it's going to be mass 1 times mass 2 is going to be involved in our expression here for Fg. And then the question is, what happens to the radius? Like, how is the radius involved in this? I love overhearing this stuff from the hallway. How are you so stupid? So the distance between these things. The distance between these things is currently 2. I'm going to go back down to 100 kilograms. Keep our numbers more reasonable. I muted it, so it's gone. Do you want it back?
Yes.
Fine. It does kind of. Okay, so here we are at 100 kilos each and 2 meters apart. Should we put them 1 meter apart? No, let's give them 2 meters apart. I like that number better. Yeah, it makes it sound for everything. So, I'm at 2 meters. And that's my force. What is going to happen if I double the distance between them? do you think? Yes.
It's going to, the number will, like the force of gravity will go down significantly.
Let's find out.
Yeah,
It did. It dropped a lot. Question is, did it drop? So it's going down. As distance increases, force goes down. So how does that show up mathematically?
you get a ratio.
You get a ratio, kind of, yes. How could we add something to this expression? How could we add the distance between them to this expression? Not different. Actually, unfortunately, it's not different. Dang it, Gercuret. Yes, it is on the board. Oh, Manuel. Why did you wrecked it? Gercuret wrecked it, and I didn't wreck it. Dang it, Manuel!
I see FG minus FA.
Okay. Yeah, that's it right there. Yeah. The thing that I wanted you guys to figure out on your own, and maybe a little bit here, is as you decrease, if you're increasing the distance and it decreases the force of gravity, there has to be what's called an inverse relationship between Fg and that distance, which means that distance is going to have to show up down here in the denominator. As the denominator gets larger, the force of gravity goes down. This is how that's going to show up. And the question then is, well, how exactly is it going to show up? If I have doubled the distance, what has that done to the force of gravity? More specific, we already know it decreased. How much? How does this number, I mean, you know the question I'm going to ask, how does this number relate to the first number? No. How does, no, I want a concrete answer. How does this number relate to the first number? 1.67 times 10 to the negative 7. It's 1/4. So if I double the distance and I get 1/4 of the force, what do I have to do here to the r to make doubling it equal to 1/4, not 1/2? I gotta square it. So then if I triple the distance that was originally between them, what do you think is going to happen? It's going to be 1/9, yeah. So it was at 2, now I need to go to 6. How does this number relate? Punch in your calculator, see what we get. Thank you. Wait for it. There it is. Oh, there it is. How does that number relate? And don't just tell me it's smaller. Verify that Luis is right, that it's 1/9 what we started. Turns out you did it? Okay. So that is there's a few ways that you could play with this thing. You could have graphed things. You could have, I just wanted, at the start of this whole next section, I wanted you guys to take a look at actually playing with these values. Now the question is, where does that first number come from anyway? Because these numbers are ridiculous. 1.85 times 10 to the negative 8, 1.67 times 10 to the negative 7. Where are these things coming from? Because the masses were each 100 kilograms, and we're talking like 6 meters apart. So 100 times 100 divided by 36 is not 1.85 times 10 to the negative 8. So there must be something right here, some multiplier, that is going to alter our force of gravity. And yes, as Manuel already pointed out, it is currently written on the board because one of the physics 12s was coming down here at lunch to get some help. So let's flip the page. Let's just get right into it. Good eye, Manuel. Good eye. So, gravity. Oh. It was. And I said, good eye. Like, you're the only one that noticed it. And this is what we've been doing for the last 20 minutes. I was complimenting you. Like, not even sarcastically. I was, like, legitimately complimenting you. So, gravity. What you need to know about gravity is gravity attracts any two objects depending on two things: their masses and the distance between their centers. Relative, like, we had not to talk about another object. It's always got to be relative to another object. We're gonna find. Let's find out. Actually, Manuel, since you're the one that wants to do this,
We have like an effect on everything, but it's so exponential.
calculatably, yes. Measurably, no.
Wow.
Because if I go back here, we can actually, let's do it right here. Connor, do you know what your mass is?
Yeah, maybe 6 kilograms.
Manuel, do you know yours?
I am 77.
How far apart are you both right now?
Like a quarter of a meter.
Can
No, like a meter. How is
center
a meter
center to center to center? Zaid, measure.
Don't do it. Oh my god!
Okay, gentlemen, put yourselves a meter apart. So Connor, well, Manuel, you stay where you are. Connor can slide. So your centers are a meter apart.
Come towards me.
No, come in, not towards you, in.
No, not that far. Yeah, they are in my center.
Okay, so
There.
according to this applet, this is the that was the force of gravity between you. 0.00000365254 newtons.
That's something. Because we're affected by Earth's gravity, how are we affected by Jupiter's? Oh, that's a good point.
That's
more than one before. No, because no.
You are constantly, okay, so you bring up a good point. You are constantly under the effect of gravity of every other object in the universe. But the vast majority of them aren't measurable. Because we've already established, as the distance increases, it's squared. It's 1 over r squared is what's happening here.
So the only thing that's really
But it's still there, yes.
awesome.
It's still there. It's never practically, like from a physics standpoint, it's 0. Because it may as well be, even this number right here, mathematically, is that number 0? No. But practically, we can ignore it. You would never know. If Connor just ceased to exist, like right now, boom, we have vaporized Connor. Manuel, you would not notice a change. Hold on. You would not notice a change. You wouldn't like all of a sudden be like, oh, I'm relaxed now because I was being pushed to the right before. It's not about, again, we've already established, it's not about the space he takes up. If we shrunk Connor to a point mass with the same, like if we just took him and went, that has this, to a pinhead that has the same mass as Connor, Manuel, no, these are all good questions. If we shrunk Connor to the size of a pinhead, and we placed that pinhead with the same mass at the center of, like where Connor is in space, it would have the same effect on you. Because we've already established it has no bearing on how physically expansive the object is. It's just solely dependent on the mass. So like a black hole, for example, is a point mass in space. It's a singularity. It has no dimensionality to it. Now the event horizon of a black hole is a different story. But like actually the black hole itself is it is a single infinitesimally small point in space with a massive mass. And so practically it has a large gravitational pull on everything around it, even though like the radius is almost nothing. The event horizon of a black hole is very big. And that's just the area with which nothing can escape. But that's not the surface of it. It doesn't have a surface.
How are they related?
Like, it's not ground you could stand on.
No. But how are they related then?
How is what related?
The singularity to the event horizon.
The more mass there is, the larger the event horizon is.
Okay, so.
But that mass
because
isn't,
it has so much force pulling on it, it just revolves.
because its gravitational force is so big.
Okay.
Okay, so, but you talk about the revolving piece, Connor. That's a concept called circular motion, and you'll actually study that in Physics 12. Practically speaking, right now we're just talking about gravity. Newton's law of universal gravitation. So we've established that the force of gravity, and this isn't just, we're not doing mg anymore. Mg was little g. That was true if we knew what little g was. I mean, it is true still, but what is little g? How do we find little g at all these different places? I told you what little g for the moon was. I told you what little g was for Jupiter, the sun, and Earth, at or near its surface. But we haven't actually figured out how we're going to calculate that. Newton discovered, or he developed this law of universal gravitation. We have the big M, little m over r squared piece. Now, I called this M1 and M2. You can call it big M and little m. It doesn't ultimately matter. You just need to recognize that these two m's are for the two different objects. They could be numerically the same, but one represents one object and one represents the other. There is a value out front here called big G. Big G, which makes it sound super gangster. But it's not. It's actually really small. Big G has a name. It's called the universal gravitational constant.
What is that?
It is a universal gravitational constant.
What is that equal?
Oh, I'll give it to you in a second on the second line.
And does the R have to be written like that?
Lowercase? Yes, because uppercase R is different.
I'm in the way you actually done your little thing. Look at the R on the paper.
It's just how I write, man.
Okay, but
That's how I write.
do.
You're right, some of them do. This is just how I'm writing. You're right. I mean, it's not a bad question. Because T, I've done a little bit of a cursive one. I do my X's a little cursive, so you can tell that it's not multiplication or addition. No, R is just R. The difference here is going to be like a uppercase or lowercase. My L's are all cursive because otherwise it looks like a 1. But R doesn't mimic anything numerically, and so R is just R. The universal gravitational constant is the same everywhere. That's what universal means. And we have figured out that value experimentally. That value is 6.67 times 10 to the negative 11. It's actually on your formula sheet. And it has units of Newton meters squared per second squared. The universal gravitational constant of the universe. Yeah, basically, it's just a value that is true everywhere.
Wait, does that bring it?
It's a, how do I explain this better? Like, I don't know. It doesn't necessarily mean anything. It is a.
Is it like Avogadro?
Yeah. Well, kind of. No, Avogadro's number is the number of objects in a mole. We defined that. We defined that 1 mole of something is 6.02 times 10 to the 23, right? Is that the number? Something like that? We defined that. This one, we actually measured. This is a measurable trait of our universe. And we started using this applet, we started the process of finding out what this G value is. Because we were able to figure out that as I adjusted the masses, if I doubled the masses, it doubled the force of gravity. If I halved the masses, it would have halved the force of gravity. If I doubled the distance at 1/4 the gravity. So we got this piece here. We got the mm over r squared thing here. So then what these guys actually did, they did the experiment that we had in our little applet. They were able to measure what the force inward on these two objects was. They had two objects hanging there in space, and they said, okay, they're this far apart. We know their masses. Let's measure it. They discovered that in order for their number to be accurate, the force this expression here had to be multiplied by this g value, 6.67 times 10 to the negative 11. And so they're like, okay, that's interesting. These two objects had this this multiplier that I had to add to the expression to calculate the force that I measured. You follow? Okay. So then what they did was they then started other pairs of objects. And they discovered that it didn't matter what the objects were. It didn't matter what their differences in mass were. It didn't matter how far, as you change the distances. This value, this multiplier g, had to be present for all of these objects within the lab, and even talking about objects in orbit. This value has to be there. So they said, okay, this must then be a universal constant. There are a few of them in the universe that we have. One of them is this, and it's true everywhere that we've seen. What are the other ones? There's one called the permeability of free space. Basically how vacuumous a vacuum actually is, like how you travel through a vacuum versus how you travel through other mediums. There's a constant there that measures that. I can show you this. You know what? Let's pull up the list briefly. I want universal constants. Sorry? That's not a universal constant. That's an expression. It's also true, but it's different. It's an equation. So here, c, the speed of light. Duh. That's another universal gravitational constant. Another universal constant. I don't want this video. I just want these things here. Avogadro's number. It's a constant. We've defined that one. There's a gas constant. I think you do gas constant in Chem 12. There's this R value here. It talks about. It relates it's Pivnert, PV equals nRT, where you've got the relationship between the pressure, the volume, the number of moles, and the temperature of a gas. That the way that those things relate to each other, you have to have this multiplier R in there to make them relate properly mathematically. There's something called the Boltzmann constant. There are more. There's a bigger list. There's a magnetic constant called mu naught. There's an electrical constant. There's a Planck constant. There's the elementary charge, which is the charge on an electron. That's a universal constant. The proton mass, the fine structure constant. There's lots of these things. The Faraday constant, which is all about inductance, which you'll learn about in Physics 12. There's a whole bunch of these constants. And the interesting thing is if any of these constants changed at all anywhere, our universe would cease to exist the way it is. These are all exactly what they are everywhere in the universe, and it's the only way the universe actually is held together. It's pretty cool. So this is just another one of those universal constants. In this case, it's gravity, 6.67 times 10 to the negative 11, and we figured that out experimentally. It's measurable. So then these two m's, big M is the mass of the first object. And little m is the mass of the second object. And we don't use the letter D, we use R, even though we're talking about the distance between their centers. We talk about that R as the radius, which is the distance between centers. And the reason we talk about this R, the distance between their centers, as being a radius, is because usually these two objects, one of them is in orbit around the other one. And an orbit is almost a circle. And so we talk about the radius of that circle, which is the distance from the center to the center, which is why we call it R. Technically, orbits aren't perfect circles. They're ellipses, but that's okay. They may as well be circles. So we're just going to do a couple examples calculating things using this relationship. And then I'm going to give you a bunch of questions where you can play with this. And we're going to call it a day. So here we go. What is the force of gravity exerted on a 70-kilogram astronaut standing on the Earth's surface? On the Earth's surface, we know we've got a way to calculate this already, right? Fg is just, if I tell you that you're on the Earth's surface, the expression we could use for force of gravity is what? M times G, where G is what? 9.8. Okay? So let's do that first. Fg equals mg. So that's we're going to get our 70 kilograms times 9.81. What's the force of gravity on our astronaut on the Earth's surface? 686.7 newtons. Okay, let's use our new expression now. Our new expression is the universal law of gravitation. Fg equals big G, big M, little m over r squared. Now, the constants that you're going to need are on your formula sheet. The mass of the Earth is 5.98 times 10 to the 24 kilograms. And its radius, the distance from the center of the Earth to the surface of the Earth, is, on average, 6.38 times 10 to the 6 meters. Now, that number is a little bit different at the North Pole and South Pole than it is at the equator, because the Earth's a little fatter at the equator because it's spinning like this. It's revolving. And so its middle is a little chubbier. But on average, this is a good value. So let's plug these values in. So we're going to have our 6.67 times 10 to the negative 11. You're going to have to get real comfortable using your calculator for scientific notation. Brackets are going to be totally necessary. The mass of the Earth is 5.98 times 10 to the 24. The mass of our astronaut is 70. The radius of the Earth is approximately 6.38 times 10 to the 6 meters. Punch that into your calculator appropriately using brackets and things. Canmore, wake up. And tell me what you get. I want you all to be comfortable with your calculator here. Grab your calculators. This is where a two-line display scientific calculator is totally necessary. What should that number be? No. What should the number be? We calculated, okay, this is still force of gravity. This answer should be what?
686.7 newtons.
It should be exactly the same. We're just using two different equations for the same value. It's still Fg. So if we don't get that, we made a horrible mistake somewhere. Do we get the same value? Sorry? Or are we still punching things out? Should be this. We should get the same number for this as we did for this. You got 0.8? 685.9. So we're out by 0.6 of a Newton. That's perfect. As these aren't, this value isn't perfect. Oh, that's should be our source. Ooh, I forgot to square that bottom value. Radius squared. So lots of punching buttons in the calculator. 15? Yeah. Think you've done something horribly wrong? Okay, let's jump in here. 6.67 times 10 to the negative 11 bracket 5.98 times 10 to the, what is it, 24? Yeah. Times 70 divided by 6.38 times 10 to the 6. Oops, I should put brackets around that. Squared. Why is it not exact? Well, the radius of the Earth is not the same everywhere. We're going to be out by a little bit. The 9.81 that we used before is not an exact value. So here's what's interesting. What is 685.9 newtons? Hey, Carolyn, what's up? Doing which?
The hoodies for school. Maybe she.
The which?
The hoodies for like school, like sweat.
Oh, the hoodies and stuff. Yeah, that's something we do. Can we talk about it tomorrow?
Yeah.
Okay. That's the easier way to do it. Okay. Questions, comments, concerns? We are concerned? Why are you concerned?
I think that's screwed up on brackets somehow.
Well, every value just needs the other brackets.
Look at this. Well, no, because when I hit the exponent function, it gives me another bracket that I have to like actually close. I think close it.
Okay, well, bracket.
Okay, let's do it together, Mr.
No, I really don't want to do it together.
I got like 4 billion and
Yeah, this is why I want all of you to do it. Make sure we know how to use a calculator. Bracket, 6.67 times 10 to the negative 11. Then I had to close the bracket.
Completely different hold up, Mr. Rudolph. That's maybe where I went wrong. You hit a completely different button than I did.
We have a completely different calculator.
How do you know that?
Because I can see your calculator.
So yours is pink, mine is black.
Six 6.38 times 10 to the 6. And then you have to square that in the denominator.
Yeah, I am. Okay, so that's
Now we're good? No, yeah, we're good. Okay.
okay, hold on.
Gentlemen in the back corner, we're good. Tristan, Hershawn, James, Brendan, Cohen, and crew. Eric, Niraj, Kanwar, we're all good? I know you do. That's why I just said it. Sometimes one of you speaks for all of you. Usually it's you, Eric.
No, it's Cohen.
Often it's Cohen, but usually, well, when Cohen wasn't here, it was Eric who spoke for everybody. Okay, number 2. What is the force of gravity acting on a 70-kilogram astronaut at an altitude of 6.38 times 10 to the 6 meters? What does altitude mean? Height. Height above what? Height. Altitude is height above a surface.
usually about the ocean level.
So, there's my Earth. This astronaut was on the Earth's surface, this first one. Connor. The first astronaut here was on the Earth's surface. This distance here is 6.38 times 10 to the 6. Our new astronaut is out here. an altitude of 6.38 times 10 to the 6. So what's this total distance here? That distance there is the radius, 6.38 times 10 to the 6 meters. This distance right here, we're told in the question, is an altitude of 6.38 times 10 to the 6 meters.
What's the total you're asking?
What's the total distance between them?
Okay, well, if you add them together, it'd be 2 times 5 maybe?
Well, it's just going to be 2 times 6.38 times 10 to the 6, whatever that is, right? So we can just, what the difference, the reason example 2 exists is to show you the difference here. Now, the language in the question. The altitude is this, which means you have to take into account the radius of the Earth and then add to it that distance there. So FG then is going to be 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 times 70 divided by 2 times 6.38 times 10 to the 6 all squared. What's the force of gravity on this dude? Zero, is that value?
171, but I'm not sure if that's fully right.
That is
171.
171.5.
Yeah.
See if someone can verify that. Usually the verification comes from over here in the front 2 rows. Someone else verify that value.
Yeah.
Tanjo, Naya, both? Okay. We can also think about it here, about the relationship we did before. What did we do to this distance compared to this distance? This distance is double. So this should be a 1/4 of this. Well, what's 685.9 divided by 4? Assuming that neither of these values were rounded, and I think they both were.
171.5.
There you go. Love it. Things are working out the way they're supposed to be. Example number 3. 2 physics lab partners. Oh, hey, we basically did this one. Let's actually find the value. Connor and Manuel are sitting side by side. One of them has a mass of 55 kilograms, the other one is 65. If they're sitting 50 centimeters apart, what is the irresistible force of attraction between them? This irresistible should be in quotes. Let's actually crunch the numbers here. Fg equals gmm over r squared. You should always include the formula here. And now let's fill it in. Big G is 6.67 times 10 to the negative 11. One of the masses is 55. The other one was 65. Thank you. What is the distance between their centers? But it should it go in as 50 centimeters? We always, what's the scientific standard unit for distance?
5 meters.
Meters, so it should be 0.5 meters. What is the force of gravity between these 2 lab partners? always a pull. It's always a pull. It's always an attractive force. Yo, yo. What's up? To who? Okay. Bye. Abdul. Mr. Sadu wants to see you. There's only 3 minutes left in class, so take your stuff with you. The homework is going to be this page. Okay. What's the value? What's FG? Sorry? Sorry? You have a quiz tomorrow, yeah. Everything before this, everything before today. 9 point. What's the value here?
9.53, 1 times 10 to the negative 7. Did I get it?
It is 9.53 times 10 to the negative 7.
I got it.
Well done.
Thank you.
Okay, so this number, very, 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 very small. You don't notice it. If that lab partner, just one of them just disappeared, you'd never notice. Practically, like from a gravitational standpoint. Okay.
This is a 7? Like,
These guys here, these are typical problems. I want you guys to try these two for homework. And I want you guys to take a look at these 11 questions. And I'd like you to do these for homework as well. Now, before you freak out and say, oh man, I have 13 questions for homework and we have a quiz tomorrow. Mr. Dawidoff, how could you do this to me? I am not going to be here tomorrow, which means you can safely assume that the person coming in for me has no idea about any of this. So all I'm assigning tomorrow for the TOC to give you is a quiz, which means as soon as you finish the quiz, you will have time to work on this, and we're going to go over this on Monday. So the homework that I'm assigned, these 13 questions are due Monday, which I think is totally reasonable. Eric. No, today's lesson is not on the quiz. It's just Newton's 3 laws. That's it. This is due on Monday.